We're privileged to have Ivan Deutch, Distinguished and Regents Professor. Thank you so much. Everyone, of course, is finally very excited about quantum information systems and its impact, financial impact on New Mexico in particular. So I'm really excited to hear your perspective on that.
Very good. Thank you. Anyway, it's a pleasure for me to be here. I'm actually a little bit um, intimidated to be here because I'm actually not someone who does high performance computing. God, I haven't, written something since I wrote something in Fortran, God knows when. So this is work that we'll talk about that's really done by my postdocs and students. So don't ask me some really hard questions about high performance computing. In any event, so I'm the director of the Center for Quantum Information and Control, CQUIC. I'm a professor in the Department of Physics and Astronomy. And so I want to maybe use this time to tell you, because you might be curious, what quantum information is, what quantum computing is, and how we use CARC in the ways to help our research. So this might be a bit of a light talk. So let me just tell you, so the field that we're in is called quantum information science. It's really a interdisciplinary field. I don't know if someone's admitting them. Okay, good. It's really an interdisciplinary field that, by its very name, combines quantum physics with information science. And so I wasn't trained in this field. It didn't exist when I got my PhD in 1992. It kind of was born really in 1994, and I've been working on it ever since I came to UNM. And it's been a lot of fun to learn a lot of new things. So sort of the pillars, quantum information science is interesting because it is this interface between fundamental science and technology. It goes both ways. So some of the technologies that this impacts include quantum computation and simulation, communication, and sensing and metrology. The idea of quantum information science is that we want to use the power of what happens in the microscopic world to process information in completely different ways than if that information was governed by the laws of Newton, the classical physics laws that we learn in Physics 1. And that enables computation that goes beyond what we can solve in polynomial time according to the usual laws of complexity theory. It allows us to have communications that are, in principle, secure to an eavesdropper according to the laws of physics, that if there was an eavesdropper, we would know physics would tell us. That's called quantum key distribution. And also, we process information in a way in which we do measurements. So, for example, detecting gravity waves. We can use the principles of quantum information to detect these tiny, tiny, tiny signals above the noise that we would have expected if we didn't harness the full power of quantum mechanics. So those are the technological applications, but also the information theoretic perspectives helps us to think about science. It helps us to understand, what is quantum mechanics telling us? What is the wave function? It's an information theoretic perspective. So it's informed our thinking about the physical world as well. And that's been really new and exciting for me. So why is quantum information different than classical information? So we think about processing digital information in terms of bits, a two-state system, a 0 or 1, a true or false. Whereas in the quantum world, we have this thing called superposition, where the state of a quantum system can exist in sort of a quantum maybe space between 0 and 1 that has a chance of being 0 or a chance of being 1, but it's sort of somewhere in between. And every point on this sphere is what we call a quantum bit or a qubit. And every point on that sphere is a possible quantum state of a physical object, like one electron. And the way I like to think about it is the following. You know, what is the solution to x squared plus 1 equals 0? What is x? Well, x is the square root of -1, which is I. It has no meaning if we had real numbers, but if we have this new algebraic structure that allows us to go beyond real numbers, we can solve equations that we couldn't solve otherwise. And this algebraic structure between 0 and 1 gives us new logical operations like the square root of naught. So naught would take you from 0 to 1, but the square root of naught takes you halfway between 0 and 1. If you do it twice, you get naught. That's a perfectly good quantum logical operation. There are new logical operations, and that's powerful. The other thing that we have is this thing called entanglement, which you might have heard about. And I'll keep louder now, so I have to go faster. Which involves correlations between particles. And famously, Einstein called the spooky action at a distance. I think it gives you the wrong impression of what's going on. There is no action at a distance. We cannot send signals faster than the speed of light with entanglement. Never believe anyone who tells you otherwise. But there are very strong correlations that exist that are different than these current correlations where we know one is green or one is red. And those correlations are very powerful correlations. And in particular, it allows us to have superpositions, not just 0 and 1, but the state of a whole quantum register. So we can have a situation where, say, we have 3 quantum bits. Those 3 quantum bits can, say, be 0 or 1, but they can be in superposition. And when you have 3 bits, you have 8 different digital sequences. So I can have this is a quantum state, which is a superposition of 8 different quantum registers. And if I had a quantum register with n qubits, it would have 2 to the n different possibilities that all can exist in superposition. And there's no way to describe that state efficiently. It takes an exponential amount of information to specify the state of the system. But the world works this way. So the physical devices are processing this if we can create this kind of entangled state of n qubits. So some of the applications that we want to do include quantum simulation. So Richard Feynman is one of the great physicists of the 20th century, and he famously mused about the idea of a quantum computer. That he said the reason he mused about a quantum computer was that he wanted to study material science. He wanted to study matter, and the description of the matter involves this exponential description, and there's no way to efficiently simulate that on the computers they had. Even with Carsey, they couldn't do it, but they certainly couldn't do it in 1981. And he said, wouldn't it be great if the computer itself was operating according to the laws of quantum mechanics that we can control? Now, of course, silicon does operate according to the laws of quantum mechanics, but in a way that's not fully harnessing the full power, because it's a chunk of material. There's phonons, there's dirt, there's all kinds of things. We needed a much more isolated system to do that. Another example is, as I said, metrology. Metrology, so Carl Caves is a distinguished emeritus professor here. He is really the father of this, had this incredible idea about how you can improve the sensitivity of LIGO, which is the interferometer used to detect gravity waves. It was just a germ of an idea when Carl was a PhD student in around 1980. But he had this idea that if we can use entanglement, we can improve the sensitivity with which we can detect these things beyond the kind of noise that's intrinsic to this system. So that's another very important example is quantum computing. So quantum computing is the idea that I'm going to encode the answer to my algorithm in this quantum state, and then I'm going to measure which register I'm in. 0001, 101 is the answer to the problem. And Peter Shor, was a mathematician who at that time was at Bell Labs, showed that you could use this to break all cryptography because all RSA cryptography is based on the hardness of factoring numbers into its primes. And Peter Shor showed how with a quantum computer, you could factor those numbers in a snap. There goes your credit card. Q day is coming. That's what we call it. And people are worried about it. It's not going to happen for another decade or so, but it's going to happen. So, a quantum computer looks kind of like a computer. You have what we call quantum gates. They're not the usual logic. Well, they could have the usual logic of and or nor or, but they have these other things like the square root of not in them, or things that are called Hadamard or X. And this is a controlled, this is a controlled not or an exclusive or. We flip one qubit conditioned on the state of another. So this is hardware, right? That's under the hood. Something is storing that quantum information. It could be spins in a solid, it could be individual atoms in a gas, it could be superconductings. What a quantum computer is, we still don't know. There's a big fight out there. And it's IBM versus Google versus the startups, IonQ, Quantinuum, Quera, the like. They're coming to Albuquerque. Some of them are here already. Okay. I will quickly then tell you what the heck do we do on CAR-C to help us do some of this research. So one of the things that I've worked on in my group is what's called quantum optimal control. So the idea of quantum optimal control is that you want to make a quantum logic gate that I said it's in the hardware, and you have to do that by applying pulses of microwaves or lasers in some time-dependent fashion that drives the system, evolves the system to do the right logical operation. You want to do that in the physical system that you have, depending on what handles you have to hold on to it and move it around. And you want to optimize that. And there's some objective function that you want to optimize over, and calculating that objective function is complex because you have these large dimensional systems. So we can't really do it efficiently on, the laptop. So we use CAR-C to help us. This is an open loop control problem. We're basically solving the Schrodinger equation and sort of climbing the mountains to try to find the peaks and use that to be able to optimize our gates. So that's one example. Another example is in quantum simulation. So I said we want to simulate matter. Feynman said, well, that's hard to do because we need an exponential amount of storage to store the quantum state. However, there are some cases where we don't need all that exponential amount. We can kind of have a more compressed description, which might say we have limited entanglement in the system. And if we can quantify the state by the amount of entanglement, we can compress our description and sort of see how well that compressed description works. And we use that to simulate these many body states to sort of understand where the boundary of complexity lies. Where is it really hard and where is it easy? We need to know that. What is a quantum computer really going to be good for? Another example is based on parameter estimation. That is a kind of metrology. So suppose I want to measure a magnetic field. I don't know what direction that magnetic field is in or its magnitude. It's a magnetometer. We can do that by seeing how a set of magnetic atoms spin around in that magnetic field and measure them with a laser beam that passes through the gas that gives an index of refraction that depends on how the atoms are moving. But we don't know what direction the atoms are spinning around or how fast they're spinning around. So what we want to do is drive the atoms in a different way and get a measurement record that from which we can try to deduce the unknown parameter. So we have some likelihood function. In the end of the day, what we're doing in this case, again, is a kind of optimization, a kind of maximum likelihood estimation. And the details don't matter, but I just put this, my student Alejandro Garcia put this together for me just as an example of what he's done on the Easley cluster and the comparison between, what he could do on his laptop versus what he can do on car C. What would have taken, over a day on his laptop took him 3 hours on car C. Now, like I said, we're not the most professional high performance computing people. We probably could do better, but this just gives you a flavor. I really should have had a picture of my students. I apologize to the people in my group whose name, but they include Alejandro Garcia and Srinidhi Pawar, Andrew Forbes, Vikas Bhushamavari, Ivy Gunther, and many others who are all using car C, and it's essential to what we do. So I'll stop there and take any questions. Thank you. Yes.
So Deutsch, for a computer science faculty or students who want to get quantum computing, what would you recommend?
It's a good question. We need to do better at UNM. So we have one course currently called Introduction to Quantum Information Science, which is cross-listed between ECE, the Electrical Computer Engineering Department, and Physics and Astronomy. It's an introductory course. It doesn't require any physics, beyond, basic. It's a intro course that is at the level of seniors, basically, maybe juniors, and early first semester graduate students. That's really the entryway to the more advanced courses. But it is very much on my agenda and the agenda. We need to broaden our undergraduate curriculum because there's so much here. As you can see, I'm a passionate guy, and I would love to be able to get out in front of a lot of people to, share these ideas, because it's really fascinating. It brings together so many different things. So it's necessary for us to improve that, and it's on the agenda to make it happen. Yes.
I feel like this is gonna be a confused question, so let me apologize ahead of time. But on the kind of the simulation
Yeah.
and the idea of compressing the representations
Right.
of the quantum state, I'm trying to think about it, like in classical information theory, your data is it's comprised of the bits, and then the
Right.
information is kind of like the probability distribution of what
Right.
it'll look like.
Right.
In quantum, the data is a probability distribution.
Yeah, you're right. It is very tricky. And so it's really a question of there are different, the thing that's different in quantum mechanics is that there's not one probability distribution. There's depending on what you measure, you see different probability distributions. So the standard, if we wrote the representation in what we call the computational basis, then we might have an exponential amount. But if we write it in a different representation, which are known as matrix product states, then we have a different probability distribution. And by using that different probability distribution, we might have things more compressed, where some of the probabilities are so small that we can neglect them. And there are multiple different representations with different probability distributions in the quantum world.
So on those kind of I guess you're keeping track of the matrix operations.
Yes.
On a classic computer, one
Yeah.
might get expensive. from all of those?
It does. I mean, and that's sort of what we're looking at. How expensive does it get? So the question is, are those matrices small matrices or are they big matrices? If they get big and if the dimension of those matrices start growing exponentially with this number of bits, we're screwed. We can't simulate it anymore. But if we can truncate and keep the matrices small, then we have, if that's a good approximation, we say, well, actually, even though the system might have been complex, it's actually, there's a simple description of it.
So the work is a little bit on the matrix, actually representing the matrix.
That's right. And how well we can truncate them. Yeah,
Thank you.
my pleasure.
To self-promote this for a second, so we are developing a quantum computation course targeted at computer science students, computational,
Cool.
which is hopefully
Right.
quantum the physics approach. But
I'm delighted to hear that.
it's so much fun. It's to go from nothing but linear algebra to the block sphere is
Right.
it's just beautiful.
Great. All right. Thanks, everybody.
Thank you.